All right, well, yeah, let's go ahead and get started. So thanks for everyone for coming to this week's BTPC Idea Series talk. Today we're happy to have Stephen Carr, our recent addition to the BTPC. And yeah, so he's going to be telling us about designing Hamiltonians with twistronics. Go for it.
Thanks, David. Yeah, so I'm really excited to be here today, and thanks everyone for coming. The goal today is to kind of give an introduction to this emerging field in nanomaterials research and make some connections to topics in theoretical physics that are hopefully exciting to the listeners. So let's begin. You can see this kind of a background splash picture. It's 3 layers of graphene with different colors. And this is kind of be the motivation for the introduction, which is why do we care about 2D materials? So this slide here shows an example of 3 different types of crystals that come up in nature. So these are all carbon crystal structures. The first one is a diamond, which is 3D. And this makes up most of crystals that we deal with. Our computers are made out of 3-dimensional crystals like silicon and copper. And they're basically characterized by having covalent chemical bonds that go in all directions, X, Y, and Z. Now, there are certain types of 3D materials that don't have this sort of 3-dimensionality built into the chemical bonding structure. And these are often called layered or quasi-2-dimensional materials. Graphite is a very popular example. Other examples are some of the perovskites and some of the high TC superconductors. Basically, there are planes of atoms that are more strongly bonded in plane than they are out of some atomic plane. And in this case, you would say that in this drawing, the bonds between these carbon atoms are strong. It's a chemical bond, so it has a solid line. And the interlayer coupling between these 2D layers is weak. It's a van der Waals coupling, which is mostly dominated by London dispersion forces. So it has this weak dashed line. Now, if we go a little bit deeper, we can actually take single layers out of some of these materials, these so-called van der Waals materials, and we can make them into 2-dimensional materials. And a 2-dimensional material is different than a layered material because unlike these layered materials, the 2-dimensional materials have no z-axis. So although graphite is very anisotropic, you can still go in the z direction. You can still have a z momentum, for example, for the electrons. A 2D material is truly a 2-dimensional object. And usually if you can confine the electrons into this material, they're going to see only two degrees of freedom, the x and the y degree of freedom. And so that makes them very different. So graphene was first isolated in 2004. And over the next decade, there is a lot of work done on experimental progress to make these materials very clean and have very good transport properties. And about a decade later, in 2013, there was this idea that you could use the 2D materials as building blocks for metamaterials that had custom physics and electronics properties. So there's this famous review article by the Cambridge. Oh, the UK group. Sometimes I forget which university they work at. I really should remember. And they had this nice review article where they talked about how you could have multiple types of 2D materials and you could stack them together like a Lego structure. However, the idea here was that graphene on top of, say, hexagonal boron nitride on top of molybdenum disulfide, they would share properties with each other. And so you'd have the top layer be a certain property, the bottom layer have, say, spin orbit coupling, and the middle layer be an insulator. And these things would all play together and they would combine and create a new material with some sort of average of all 3 properties, which might be useful. However, in practice, when people started making these, a different problem emerged. And that's that these things did not link together like Lego blocks. Instead, it looked more like something you'd find at Goodwill. You had all these rugs. And the rugs, when you fabricate them and put them on top of each other, they get bunched up, they get turned, they get wrinkles, and they don't really form nice layered structures. And the reason for this is that these materials, if you fabricate them separately, the van der Waals bond is fairly weak, and so there's not really any cohesion that's going to cause them to line up perfectly when you place them on top of one another. And at first you might think this is a huge problem, but it actually is a new platform for studying condensed matter physics because here in this sort of Lego design framework, everything is inherited. You have layers and layers and layers, and each layer just shares its features with its neighbor. In this case, you can get features that are emergent, things that don't exist in the constituent monolayers, and that's because of this interference between the layers. Okay, so the most popular and famous example of this is twisted bilayer graphene. So this was an experiment in 2018 from Pablo Herrera's group at MIT. And they showed that if they were able to fabricate this 2 layers of graphene with a specific twisting angle, you can create a Moiré pattern, which is indicated in this figure as the alternating sequence of light and dark areas. So basically, when you have 2 lattices and you put them on top of each other, there are certain areas where the lattices are aligned and certain areas where they're misaligned, and this varies smoothly with space. And this creates an effective superlattice for the electrons that live at the interface of these 2 materials. And at very specific tunings, you can actually destroy all kinetic energy for the low energy electrons. And so these are basically electrons that are confined to a low energy mode centered at this white region of the Moiré pattern. And when you get rid of kinetic energy, all that's left are other terms in the Hamiltonian. So things like phonon-electron coupling and the Hubbard or Coulomb interactions. And so you'll see Mote insulating phases and superconducting phases. And this was very exciting, rightfully so. And in the last 2 years, there's been a huge explosion in experimental and theoretical papers that have really pushed the boundary of what we can do with this sort of platform. So before I get into the twisted systems themselves, I just want to talk about what the Moiré pattern comes from and the different types of Moiré patterns that you could in principle fabricate. So if you think about a 2D material, it has 2 degrees of freedom, and you can perturb those 2 degrees of freedom in 2 ways. And so there's basically 4 independent types of unique strains you can apply to the interface. 2 of those unique degrees of freedom actually create a 2-dimensional representation that represents shear straining. And so you have these 3 unique types of strains you can have in layers, in 2D layers at least. So the first one is isotropic expansion or isotropic compression, and that's when one layer becomes bigger or smaller with respect to the other in a uniform way. And so you can see this sort of triangular lattice of bright spots and dark areas because of the Moiré pattern. And then you can also have the shearing strain, which also creates a similar network, but now the way that the atoms are connected between them is different. You can see there's a little bit of more curvature at this this white stacking area. And the final method is rotation, which we showed in the previous slide. When you take 2 layers and you twist them, you can also create this sort of triangular network of bright spots. Now, these first 2 examples are not very useful from an experimental point of view because creating an isotropic or shear strain costs energy. You know, if you're going to take a layer and strain it, it's going to have more energy than if you let it sit at its normal ground state. However, rotation is unique because you can introduce a rotation to a material without causing any energy. You just take the thing and you rotate it. And the only change in the energy is due to the interface between the layers. And this is why the twist angle was used as a useful platform to create lattice mismatch and create these Moiré patterns. Now, isotropic strains still can be used. In 2013, there was a series of experiments at various groups that studied how if you put graphene on top of hexagonal boron nitride, the small lattice mismatch creates a Moiré pattern that looks like this sort of strain Moiré pattern. And this was used to show the Hofstadter butterfly effect on this emergent superlattice. Because now the length scales are so long, you can use experimentally achievable magnetic fields to see the fractal filling of the Landau spectrum. Okay. So the twist angle, though, is very, very different from, oh, sorry, is there a question?
Can you go to previous slide?
Yeah.
So you're saying that from the strain, you have the magnetic field?
Well, okay, so if you have, so when I'm talking about the Hofstadter butterfly effect,
okay.
if you figure out what magnetic field strength you need to see the Hofstadter butterfly in any significant part of your phase space, you need magnetic fields on the order of hundreds or thousands of Tesla if the length scale is a few angstroms. And that's just not achievable in practice. If your length scale is 10 nanometers or 5 nanometers, now the magnetic fields are a few Tesla, and you can do that in the laboratory. But the question you asked is also very important because I'll talk about this a little bit later. These twisted interfaces can actually represent as non-abelian gauge fields in the low energy Hamiltonian. So that has some relationship to magnetic fields.
So sorry, my question is that, well, I have paper on strain graphene. And basically the point is that you cannot have the root uniform magnetic field just by strain.
Yes. So this is not strain of an individual layer. This is an interfacial strain between 2 layers. If you look at
good. Okay, I see.
Yeah.
Okay,
so that is true. If you just strain a monolayer, you can't make a non-abelian gauge field show up. However, if you have this interfacial strain between the layers, it's not really strain, it's just the lattice mismatch. It enters into the bilayer Hamiltonian, like a magnetic field. Yeah.
Okay, thank you.
Okay. So one of the reasons from an applications point of view this is so exciting is that if you change the twist angle, you change the effective lattice size of the superlattice that is localizing electrons. And so on the right here, I have sort of this logarithmic scale showing different twist angles and different characteristic lengths for the Moiré superlattice, and some examples of effects you'll see at various length scales. On the left, I have two cartoons of maybe two experimentalists, one at Pablo's group at MIT, one at Philip's group at Columbia, or sorry, now at Harvard. They're making twisted superlattices of different colors. And not only are they different colors because they're different materials, they're also different length scales, because you can see the first superlattice, which is purple, is a very small angle. And the second superlattice, which is orange, is a very large twist angle. And you can see that the larger the twist angle is, the smaller the lattice distances between these bright spots. Yeah. So hopefully that makes it clear that this thing is not just, the twist angle is not just a source of disorder or noise, it's actually a way of controlling some effective new effective crystal that lives at the interface between the 2D materials. Okay, so at the beginning of my talk and during David's introduction, we called this Twistronics, which is a combination of the word twist and electronics. This is a word we coined in a theory paper in PRB quite a few years ago. But the main idea is that this twist angle gives you a smooth tunability of the electronic structure. And so that's kind of shown in this calculation here. This is showing the density of states in the z-axis and also in color of twisted bilayer graphene as a function of the twist angle and energy away from the Fermi level. And so we can see at the center, this is the Fermi energy. Away from the Fermi energy at large twist angles, there are these peaks. And these peaks are basically the hybridization between the original monolayer band structures due to this new effective superlattice. So if you remember in introductory condensed matter physics, you can go from a free electron to a band structure by introducing a periodic potential, because the periodic potential folds the bands into a Brillouin zone, and then the potential causes hybridization and coupling between those crossing points, avoiding crossings and opening up gaps, and making peaks in the density of states. And so we're basically seeing the same thing here. The normal density of states for graphene is a V. It's a perfect V coming from the Dirac Cones. When you introduce a superlattice, you fold that band structure up and they start hybridizing. And these peaks are basically the Van Hove singularities coming from the new metallic or insulating bands, depending on how you want to talk about how big the band gap is, in this new effective crystal. And if you go to a small enough angle, you can get lucky and have these bands hybridize just right, and you will form a double Van Hove singularity, which is basically a flat band, which creates a gigantic enhancement in the correlation effects. Okay. So my next few slides, I'm just going to talk a little bit about how we model these materials. The point of this talk isn't really to talk about how we modeled this from first principles. I just want to give some sense of how the technique is done. And then the rest of the talk will be talking about effects and implications for this sort of material and what it means for condensed matter physics, as well as physics in a more broader sense. So what I'm showing here is the connection between stacking variations between the layers and spatial variations across your Moiré superlattice. So if you have a twisted Moiré pattern, here I've zoomed in kind of in a single superlattice, a single supercell of this pattern. I've drawn a dashed line to indicate this periodicity between the aligned stacking areas and the misaligned stacking areas. And I've drawn 3 colored boxes, which I now zoom in on to look at the local stacking alignment between the layers. So the trick is basically to draw a unit cell connecting the red atoms of one layer and to look at what the shift is in the blue lattice relative to that red unit cell. And if you do this carefully across an entire Moiré pattern, you will find that there's a one-to-one correspondence between locations in the Moiré supercell and locations in this compact domain of the unit cell of one of the layers. So hopefully that's fairly clear. And I'm happy to explain this point clearly. This is really the key idea behind most of the models that do Moiré pattern calculations of electronic structure. It's functionally a transformation from a real space Hamiltonian to a local Hamiltonian that depends only on the local stacking, which here I indicate by a variable b. And the key approximation is that you're working in a small twist angle limit, a large Moiré pattern limit, where you can assume that locally the electronic structure is going to be nearly identical to the electronic structure for an aligned bilayer with that stacking configuration. So this is also illustrated on this slide. Here I have a different example of Moiré pattern. Now instead of dots, I have the lines representing, say, the bonds in graphene. And I've highlighted 2 different types of stacking areas. One is called AA, which is when the areas are aligned. This is labels represent the sublattice labels of both layers. So AA means the sublattice of layer 1, that's A, is on top of the sublattice of layer 2, which is A. AB and BA mean that the sublattice labels are eclipsed, but with opposite labeling between the layers. And if you look at these different areas and you zoom in, you'll find that the AA stacking, the lattices are basically aligned, And at AB or BA stacking, there's some relative shift between them. And because of that, the local electronic structure can vary. And the important electronic features, the thing that's causing the two Hamiltonians, the two layers that talk to each other, can vary. So that's represented in this kind of schematic or recipe Hamiltonian for a Moiré system. You have a Hamiltonian from the top layer, a Hamiltonian from the bottom layer. These are just the conventional monolayer Hamiltonians. You have some delta big T, which is some tunneling potential that tells you how much this layer wants to tunnel into its neighboring layer. And then you have some on-site potential, which is usually represented by electrostatic repulsion between the layers. And these three things, delta B, delta big T, and delta small t, can vary in space. And that's really important because it means that oftentimes one of the potentials will have a different geometric structure than the other. And so you can get very interesting fields and scalar fields and gauge fields coupling to your low energy Hamiltonians, which are in this case either Dirac cones or parabolic band edges. Okay, and I'll get to that in detail a little bit later. Okay, and this is the only slide I have about DFT, which is density functional theory, which is what I did most of my PhD work based on. And it's a way of calculating the ground state of crystal systems or isolated molecules very accurately by doing a density transformation of the Schrödinger equation. And what we're gonna know is that if you start with the configuration, you can make an aligned bilayer. I can do a calculation on that. I can extract values like the total energy of the system and the band structure of the system. And I'm not going to talk anymore about this technique or about the techniques in general. I'm just going to talk about the implications. If building these sort of models is something you're interested in doing or you want to learn more about, I was recently involved in a review article in Nature Materials that goes over a lot of the different techniques you can do to generate these sort of models. Okay. So that's the end of the introduction. I'm going to pause here if there are any questions. Otherwise, I'll go on to atomic relaxations.
I have one question.
Yes, please.
So basically, you have the field delta B and delta T, and so basically, this thing come from the effect of the other layer on this layer, right?
Yes.
So is it like if you have the system like when you study the dynamic, it is the B field and the delta B and delta T field.
Yeah, it's a mean field approximation. So this is all within the approximation that you can describe the total structure in terms of the local structure. So conceptually here, I'm not trying to treat all the individual electrons in every lattice site or the electrons around each atom as an independent element of some Fock space. I'm going to treat the quasi-particles of each layer as its new effective single particle, and then I'm going to couple them together in a very trivial way by just looking at how, at the mean field level in DFT, these potentials talk to each other.
And so then you go back. So basically, in this case, you consider the BR and TR time independent.
And they're time independent too. Yeah, that's also
okay.
True.
Thank you.
Yep. Yeah. Now there have been a few papers studying flow K engineering and these sort of things. So you introduce a time dependent field, but that doesn't really change the interlayer couplings or anything. It just is an additional time dependent factor that you add to the total Hamiltonian.
Okay. Thank you.
Okay, hey, Steven, if I can ask a question.
Yeah, sure.
This is a more naive question. So I understand that you have I'm confused why you have the vector space of states for system 1 and system 2, and why the direct sum vector space is a good description for this interacting system.
Right. So why are you able to make this sort of transformation?
Yeah. So why you're able to construct this? You go from you put the Hamiltonians and you construct a bigger matrix.
Yeah.
Increasing which is the direct sum of the two descriptions.
So it's here I'm doing a single particle approximation. So if you wanted to be extremely careful, you would do this construction not as a direct sum, but as a more complicated connection of Hilbert spaces. And so matrices would be much bigger instead of just simply adding the two blocks as the diagonal pieces. The idea here is that we're going to just ignore all the effects of correlations and quantum effects and treat it in kind of a classical mean field level to get the right band dispersions, to get the right band structure due to these chemical effects. Once you have that, you can go back later and apply all these quantum corrections to the new effective Hamiltonian. That's sort of the idea. Now, it's a very good point because the question might be, is that valid? Are these effects here shown? Do you need can you actually capture them accurately while going to a mean field level treatment? And I think the answer is yes, because what I'm trying to argue here is that these effects are basically chemical effects. The electrostatic repulsion is basically how much does the electric potential that this electron sees change depending on the geometry of the layer beneath it. And the tunneling is a very simple basis swap effect. It's just a charge transfer, basically. The layer on the bottom is able to pull some of the electron density out of the layer on the top. And so the states mix in the DFT ground state. Yeah, if we're going to talk about the fully connected correlated system, you have to build a simpler model first. And so I'm going to talk about how we build those simple models. Yeah.
Thank you.
Can I ask you a quick follow-up question then?
Yeah, sure.
So then are you saying that your DFT calculations don't account for correlation in any specific way?
That's a very good question, thank you. So the DFT calculations are accounting for correlations on the scale of the unit cell. So they have there's a DFT functional that deals with the correlations due to the electrons as they move around the atoms. However, these sort of calculations and these multi-scale techniques, until you add it by hand, there's nothing that takes care of correlations that are happening at the scale of the Moiré unit cell. So on this larger length scale. Yeah.
Thanks.
Mm-hmm. Okay. So before I go into a little bit more detail about these electronic single particle Hamiltonians, I just want to talk about atomic relaxations because in these systems, it's very important. So here I have 3 examples of images from experimental papers that have done scanning tunneling microscopy on surfaces of Moiré patterns of mostly graphene, but I think this picture down here in the bottom left is a transition metal dichalcogenide, which is a semiconductor. So what you're seeing here, let me just focus on this top left image for now, is a white and a black stacking region. Those regions are basically the AB and the BA stacking regions of graphene. And when they do this STM, they tilt the STM a little bit. And so the AB and the BA, because they have slightly different symmetry properties, they look slightly different if you tilt the angle of the microscope. They have different resolution, different contrast. And unlike what you might expect if you had 2 rigid layers twisted with respect to each other, you do not see a smooth variation of the stacking order as you go across this crystal. What you see are giant triangles of one stacking order, then a very thin line, which is basically a domain that connects that stacking order to the next one, and then another giant triangle. And as you make the angle a little bit bigger, say if you go from 0.1 degrees to 0.4 degrees, this pattern still exists, but it's scaled by the Moiré length. And as you get to larger and larger angles, I've cut this off, but if you go to about 1 degree or 2 degree, you don't see the triangles anymore at all, which means that you have smooth variation in the Moiré pattern. So what this means is that at very small angles, there's a huge amount of reconstruction happening at the interface. This isn't reconstruction like you'd see like in like a slip plane of a metal or some catalysis problem. The atoms themselves are not changing their bonding order. What's happening is there are smooth relaxations, very slight changes, just enough to change the local stacking interface. But within the plane of the graphene layer, there's no bending, there's no breaking, there's no like sharp effects happening. Everything is extremely smooth. Okay, so these other images are just more recent experiments that I've been involved with the theory for, and they're just showing that this sort of effect happens across many different materials. So this is twisted double bilayer graphene, which is an interface made from 2 bilayers of graphene. This is the transition metal dichalcogenide. This is a bilayer of graphene with a very significant amount of strain across the interface, and this causes some striping patterns in the Moiré patterns. But I'm not going to talk too much about the experiments or about it at all, even though it's very interesting. I just want to talk about how we model these interfaces and on what we can assume in general about these sort of interfaces. So to do that, we'll just use some very simple continuum elasticity theory. The idea is that we're going to think of each layer as a smooth plane and consider smooth and local deformations according to some vector field U. So if you had an atom originally in position R, you're now going to update it to position R plus U, evaluated at that original position. And to try to optimize this value of U to find what the ground state is of the system, we're going to try to optimize the energy, which is in our approximation split into 2 independent parts. So one is the straining energy or the intralayer energy, and the other is the interface energy or the interlayer energy, which we represent with a stacking fault functional, which basically tells you how much the layers like to sit at a certain stacking order. So if the 2 layers are aligned with each other, for example, in graphene, this is very unfavorable. But if they're at the AB or BA Bernal stacking, this is much more favorable. However, changing the stacking in a Moiré pattern causes some light strain in the system. Areas shrink, other areas expand. And so there's going to be a competition between these 2 terms.
I have a question.
Yeah.
Sorry, I asked too much, but basically, in this case, you consider the elasticity of the lattice, nothing to do. So R here is the lattice position, not the electron, right?
Yeah, this is a purely mechanical problem. Yeah, this is a continuum plate theory. Yeah. Now the electrons play a role in affecting the strain coefficient, but you basically extract some sort of bulk and shear moduli from a DFT calculation or from an experiment, and then you don't worry about the electrons at all.
Okay. If you have the for example, if you consider the gap state, then could so if we have the band structure with the gap, could the electrode will contribute to the deformation?
I mean, they do in some way, but that should be captured. We're doing a linear expansion of the energy. So we're basically assuming that the strain energy is captured by a quadratic term that depends on the shearing or the isotropic expansion, and that's it.
Because, for example, like in if the electron is in the gapless mode, in the gapless state, you don't really worry too much about electron. But if you have something like, for example, in quantum hole, if you have the very big gap, then basically you need to think about the deformation of the electron.
I think that's a really interesting point. So I think there is a scenario in which something like a quantum Hall effect or a Mote insulator effect would prefer a certain type of stacking, and it'll actually push the material into that stacking orientation. The model I'm doing here does not capture that effect. No.
Okay, thank you.
Yeah, that is a good point. As far as we can tell, it's not, that sort of term is not necessary for the sort of pedestrian relaxations we're seeing, but when you're in an area of regime with strong correlations, it's definitely possible. I agree.
I see.
Yeah. So here what I'm showing is the different the different numbers that come out of DFT for a stacking fault energy, which is the interlayer cohesion between the planes. So on the left here, I have a drawing of graphene and then a drawing of transition metal dichalcogenide, MOS2. And I've drawn in a thin black line the unit cell of that layer. And so this plot over here is basically the energy as a function of space if I was the second layer standing at this point of the unit cell. And so what we see for graphene is that the highest energy, I think there's a shift here where this line is drawn, so sorry about that. But the lowest energy is this black area, and that would correspond to eclipse stacking sites. Half eclipse stacking sites, so the AB or BA Bernal stacking. And the red area, which is on the corners, would correspond to aligned stacking sites, AA stacking, where the two layers are exactly the same place. And we can see a similar sort of structure for the hexagonal semiconductor MOS2. The difference here is that because of the symmetry breaking, because of the two different sublattices, you can actually break the symmetry between these two low energy AB and BA stacking orders. And this is just a line cut through the diagonal of this object, just to give you a sense of the energy scales. Basically, you can see variations on the scale of 10 to 100 MeV as a function of the stacking order. And if we put this into our continuum model, we're able to compute the relaxed structures, and they look quite pretty, and they agree extremely well with the experiments. So these are both low angle limits, and what we're seeing is an area of high energy stacking that's been compressed to a small disk, a small node. We're seeing regions of intermediate stacking that are compressed into small lines. And we're seeing large triangles or large hexagons of the lowest energy stacking that are now dominating the surface of the material. But if we look closely, there's no large deformations in the actual material. These are all very smooth and soft deformations happening on the scale of a few nanometers. So these nodes and these domain walls are on the scale of a few nanometers about. I think this is actually the nanometer scale, but I could be wrong. Yeah. Didn't put an axis label, unfortunately, or it got cut off. So this is just one other way of viewing this sort of continuum result. Here I'm plotting now not the atom positions, but the value of the interface energy as a function of space. As I go down this plot, I'm changing the twist angle. So I'm going from about 2 degrees in graphene, bilayer graphene, to about 0.05 degrees, which is very, very small twist angle. The left column is showing the energy as a function of space, where I'm keeping the Moiré length a fixed size. So if we look at these bright red AA stacking spots, we notice they stay in kind of the same place. That's how you know you're you're kind of zooming out as you make the twist angle smaller. This plot on the right is showing the opposite condition, which is I keep the real space window of my plotting fixed. And so once we get to about 0.5 degree, you can see that these AA stacking spots no longer change in size. And this is a pretty standard result from any sort of elasticity theory with a twisted boundary condition or some sort of topological defect. There's going to be some lowest energy mode, some lowest amount of curvature that you can introduce to the material. Whereas if you tried to make this, this node any smaller or made the wall any thinner, the additional curvature energy would beat the gain you would get in the interlayer energy. But the key takeaway is that at very small angles, we see examples that are very similar to the experiment and that are well described by this continuum theory. Large triangles of uniform stacking separated by thin walls of these soliton solutions of the PE. Okay, so my next section is going to be about these electrons, the Moiré potentials, and just talk a little bit about the models behind them. Are there any questions about atomic relaxation before I continue? Okay, great. And if anyone has questions, either interrupt me or we'll have some time at the end to go over anything. So let's talk about how we model electrons in the system. So again, we're going to think about the single particle limit. We're not going to worry about a large Hilbert space with many Fock states. We're just going to ask, okay, if I could model one electron and assume the rest of the electrons act in the same way, I can treat that at the mean field level and just see what that electron is going to do within the potential created by all the other electrons doing the same thing. This is a similar technique to some DFT approaches. The problem is if you use DFT directly, or if you do a tight binding model based on empirical or experimental evidence, you run into a problem at small angles, and that's that the number of atoms becomes extremely high. You get large variations in the length scale, so you have this very large Moiré length scale, but a very short atomic length scale. And you don't have a guaranteed periodicity, so the ideas of block theory and translational symmetry might not always apply. In certain cases they do, but this limits you to very specific geometric constructions of the supercell. So the general solution to this problem is to look instead towards low energy expansions, to expand the model in terms of the low energy modes instead of in terms of the geometric structure of the atoms. So let's go back to this model that we had a few slides, 10 slides ago. And now I'm going to look at the HL1 and the HL2, these monolayer Hamiltonians. What are the kind of ingredients that show up at low energies? Well, for most 2D materials, you're only going to see one of two things. You're going to see some sort of metallic like crossing, possibly a massless Dirac cone at the Fermi energy, or you're going to see a parabolic band edge like in a semiconductor. So you either have a massless Dirac Hamiltonian or you have a massive parabolic Hamiltonian. So that's pretty straightforward. Now, there are other situations that happen, but so far, at least for the materials that have been studied and modeled, these are the two regimes that have been used. And even with just these two building blocks, you can create a large amount of different structures. Okay, so now let's talk about how we do the low energy expansion. We're going to expand it in terms of the block waves of these Hamiltonians. And to do that, we have to talk about the basis, the momentum basis that we're using. So if you have two layers, and then you twist one of the layers, the lattice is going to rotate. And that means the reciprocal space of that layer also rotates. If you do the expansion around gamma, this isn't too much of a problem because the gamma points will always be at the same place, regardless of the relative rotation between the layers. However, if you do the expansion at the K point, like you would with graphene, that's where the Dirac cones live, this twist angle actually moves the K points apart in space. And so now you have this weird kind of pseudo-realistic Hamiltonian where you have two quasi-particles that have quadratic dependence on the energy, on the momentum, but there's no momentum at which when they're both equal to 0. So there's a momentum shift between the two quasi-particles. You can't find a single momentum in which both layers, both electrons will have exactly 0 energy. If you go to this layer's 0 energy point, you'll be at a high energy state of the other layer. And this enters into the structure of the low energy Hamiltonian if you do it correctly. So now let's talk about how we get these other potentials, these delta potentials or these tunneling potentials. Well, the idea is pretty simple. If you're able to just focus on a single band edge, you can think of a hybridization between them. And that hybridization has to take one of two forms, or some combination of the two. Either the two layers don't talk to each other, and they only see the electrostatic potentials. And so one of these purple bands would be the red layer, and one of the purple bands would be the blue layer, and this delta T and delta B will be negative values of each other. The other extreme is that these delta potentials are 0, and the tunneling explains everything. And so now the reason this is purple then in that case is because it's an even mixture of the top and bottom layer, split by the tunneling potential. And so this sort of model for the low energy Moiré pattern semiconductor was first presented by in a nice paper in PRL by Alan McDonald's group, citation down here. And recently, with my collaborators in the Kexirs group at Harvard, we've been working on ways of extracting this potential from arbitrary DFT calculations by doing some clever tricks with the cone sham wave functions. But that's kind of technical. So it's basically just an inverse matrix problem. You want to calculate these eigenvectors and then reverse engineer what these potentials are when you project onto just these two bands. The other thing I want to say is that once you have this model and you start building it, we might want to ask what are the states we expect to see at some of the limits. So let's go to the very small angle limit. Well, when we're in the small angle limit, you can kind of expand this harmonic potential well very accurately as a quadratic term, and you can ignore the high energy terms, the large t values, or maybe you're at the bottom of the t well or at the top of the t well, and you just have to change the sign of the energy axis. It's not a big deal. But let's say we're at the bottom of the t well, and we can say that the states that are being perturbed by things up here don't really matter. And so what we have is some effective Hamiltonian with an effective mass that's in a potential well. So we have some electron gas in a potential well. And in 2D, we expect to get eventually some sort of 2D harmonic oscillator. So this is an illustration of the 1D harmonic oscillator. These are the equations of the 2D harmonic oscillator. And the key thing to remember here is that because the twist angle controls the length scale of this potential, but does not control the height of the potential, as you change the twist angle, you're going to change this effective frequency because you're making the well more and more shallow as you make the twist angle smaller and smaller. And so we should have a tunable harmonic oscillator that follows the degeneracy sequence of the 2D harmonic oscillator, which would be 1 degenerate energy state for n equals 0, 2 for n equals 1, 3 for n equals 2, etc. So it's the number of states will grow linearly with the energy excitation. So we can do that with some of our calculations, either from type binding or from a continuum model or from DFT. And we're just going to keep track of the average band value and the average bandwidth and see how that changes as a function of twist angle. So for example, this band here, I would say that has an average value of about -30, and it has a bandwidth of about 10 or 5 MeV. Of course, the computer does a much better job than I do just looking at the picture. So when we plot this, we get something that looks like this. So what I'm showing here is each of these circles is a specific band calculation from a specific twist angle. And the twist angle is on the bottom axis, and the band average energy is on the y-axis. And the color scale is telling you how flat the band is. So the more red the circle is, that's a flatter band. And what we see is that as the twist angle gets smaller, there are these sequences of bands that become kind of a continuum. And as you get closer and closer to 0 twist angle, they become extremely flat, and they fall exactly onto these lines predicted by the quantum harmonic oscillator. And on top of that, you can check the degeneracy sequence. This n equals 0 level has exactly 1 state. The n equals 1 level has exactly 2 states. And the n equals 2 level has exactly 3 states, although you have to kind of look at that. I didn't draw the guides for the eye for that. And you can actually look at the density of states, the local density of states of these bands and see that. So here's a projection of these states on the 2D surface for each band. And so the n equals 0 level has a single band, and it has an S wave on the triangular Moiré lattice. The n equals 1 band has 2 solutions. They also sit on the triangular lattice, but they have a single node because they're kind of like P waves. This is kind of like a PX and a PY solution. And then finally, at n equals 3, you have 3 modes. They have 2 nodes because they're at the n equals 3 level. They're the next momentum. And they have more of some sort of mixture of P and D-like character projected into the 2D angular momentum space. So you can see that maybe the labeling is wrong, but it seems like these two are probably related to each other. And this one is the unique character. Yeah, and you can play this game all the way down. And you see all these very beautiful nodal patterns in the bands, as long as the bands are flat enough. Once the bands become dispersed, if you lose this, and all you see is the metal. Okay, so this was for the triangular quantum harmonic oscillator. However, there are different types of potentials that occur in these systems that, for example, could have a hexagonal symmetry. So there was a recent paper from Matea Angeli and Alan McDonald, where it's on the preprint server, but they looked at DFT and continuum calculations of a material tungsten diselenide, which is dominated by a honeycomb potential, not by a triangular potential. What you see is, again, a sort of sequence of flat bands, except now instead of the first level being a single band, it has 2 bands. And because of the honeycomb potential, it creates a Dirac cone. So we're basically fabricating artificial graphene at the interface between these layers. And this is very interesting. We can see similar things in our calculations of, in this case, molybdenum ditelluride. If you go down to 1 degree and include atomic relaxations, you can see that the first 3 bands, which basically correspond to the first 2 red bands and then the first blue band, they follow a honeycomb network. And the third band, which would be this first blue band up here, is still in the honeycomb network, but it's a higher angular momentum because it has this 3-fold nodal symmetry. However, if we go to 3 degrees and include atomic relaxations, what we find is that no longer does the honeycomb model dominate. There's another potential that's on the triangular lattice, and now it's dominating. And so the lowest band for 3 degrees is actually on the triangular lattice. The second highest band is on the honeycomb lattice, and the third highest band is some superposition of the 2. And so you can see that these potentials are competing with each other, and their competition depends on the twist angle. So why is that exciting? Well, I think this is one of the clearest examples of topological insulation coming about because of geometric competition between Hamiltonians. So I showed this picture a while ago. This is the interlayer tunneling at AA versus the electrostatic repulsion at AB and BA. The interlayer tunneling is on a triangular lattice. The electrostatic repulsion is strong on a hexagonal lattice. And as you make the twist angle very small, the atomic relaxations play a role. They confine the Moiré pattern in terms of these high energy stackings that get smushed into a small circle. And so the effective strength of the delta T potential becomes very small. However, the delta T, these electrostatic repulsions, we're creating these large triangles of uniform stacking. And so now you have these large hexagonal things that look like a honeycomb lattice. And so it makes this potential dominate. And so I've drawn a cartoon here. This is not based on data, just based on intuition and our understanding of the models. If you have an unrelaxed system, as you change the twist angle, the dominating potential doesn't change. But when you include atomic relaxations, you can actually cause a crossover. You can go from a triangular lattice to a hexagonal lattice at small angles. And this competition between the two types of geometries gives you topological insulating states. How can we see that? Well, here's another cartoon. I've drawn on the left the limit of delta T, or the triangular lattice dominating. And you have a single sequence, 1, 2, 3, 4, of the quantum harmonic oscillator. The hexagonal lattice or honeycomb lattice has a double quantum harmonic oscillator sequence, and so its bands go 2, 4, 6, 8, etc. And if you want to tune in between the two, you have to go from, if you count here, we have 1, 2 plus 3, that's 6. We have 2 plus 4, that's 6. These 6 bands actually hybridize with each other and transform into one another as you change the twisting angle. And the only way that can happen is by having this large amount of geometric frustration in the band hybridization. And this causes topological insulation. At the same time that this is happening, the bands are very flat. And as we know with twisted bilayer graphene, we see superconductivity and strongly correlated phases. And so this is a very interesting combination of both a strongly correlated regime intersecting with the topologically insulating regime. So it might be an exciting platform. Okay, this is a final slide about that topic. I'm not going to get into details. We basically made a phase space diagram of this topological insulating event. The blue areas are the triangular lattice. The orange areas are the hexagonal lattice, and these green areas in between are the topologically insulating states. And at any of the boundaries between these different colors, for example, this brown is called overlap. This is basically a topologically protected edge state. So by controlling the twist angle in these materials, you could fabricate in-plane edge states that don't require a bulk boundary condition of a material. So that might be a very, very nice platform for studying topological insulation, valleytronics, spintronics, and things like that. On the right here, I have the band structure calculations performed by my collaborator, Hao Tang, who was the lead for this project, which was quite successful and still in preparation, but should be ready soon. And these are the churn numbers for the bands. So you'll notice that the unrelaxed case, we say it's topologically trivial because the top band has 0 churn character. When you relax the system, it gets pushed into this green phase, and now it has a very complicated band structure, and it has topological insulating states. Okay. Before I finish my little spiel on the electronic structure stuff, I'm going to very quickly go through the bilayer graphene argument. Now, twisted bilayer graphene is very similar to the parabolic Hamiltonians we talked about. The only difference is that now instead of having a one-sided Hamiltonian in a potential well, you have a two-sided Hamiltonian in a potential well. And instead of having a quadratic expansion, you have the massless linear expansion of the energy. The takeaway is that, again, just like with the harmonic oscillator, if you tune the length scale just right, you're able to create these band gaps and create flat bands. The difference is because you have two sides, unlike the harmonic oscillator, where you're able to make a low energy band and then keep adding them up as you go higher in energy, you're getting these hybridizations on both sides of the band structure. And so this is why graphene has what's called a magic angle, or a precise tuning. You need the hybridization on the top and the bottom to exactly cancel each other out to create a flat band. Now, if you want to do this carefully, if you want to do it analytically, it's quite challenging. There's recently been some work in PRL from Ashwin Vishwanath's group. I didn't put the citation because I forgot, but I'm happy to share that citation if anyone wants it. They actually solved this Dirac Hamiltonian under a very specific assumption analytically, and they show that it has flat bands. But most of us do numerical calculations, and that's basically taking all these potentials that we developed and doing Fourier transforms on them and calculating the band structure in the momentum space. This is a little bit technical, but not really anything difficult. It's just careful numerics and proper transformation of all the variables that I showed in the previous slides. And including relaxations tends to be important.
Yeah, so the paper that you said with Vishna is a paper with basically they can show that the flat band analytically, but with very strained requirement.
I don't think, no, it's a, well, it's related to that. It's this chiral symmetric limit. So what you have to do is you have to turn off some of the tunneling terms. The tunneling
so
that relates to atoms of the same
basically, you need to turn off the AI
Yes,
tunneling.
that's correct. Yes.
And it's very strange because in experiment, the AI is not small compared to the IB.
That's true. It's about a factor of, it's like 30% smaller because of relaxations. But yeah, that's a pretty technical point, and that's why I didn't want to really talk about it. But that paper is not saying that you need that to be true for flat bands to exist. It just shows that when that condition is true, you can analytically derive the flat bands using complex analysis.
Yeah, that's true. That's true.
Yeah.
So it's like saying that if the condition is satisfied, you can prove this by saying that wave function satisfies the flat band analytically, similar with the Landau level. But
exactly. But in real systems, those approximations are not true. So there's always a little bit of perturbations on top of that. But they were kind of arguing that this was the minimal amount of ingredients you need to create the flat band.
Yeah. Okay.
Okay. So I'm going to skip this slide. This basically is just explaining how the relaxations affect the low energy band structure. But if anyone wants to talk about that, it's more of an experimental detail, and this is pretty well understood by the community now. But basically on the left, we have the unrelaxed band structure, and on the right, we have the relaxed band structure. So, and the other effect of these relaxations is the suppression of the magic angle. So like I said in the beginning of this bilayer graphene discussion, the flat bands are coming because of this paired hybridization between the top crossing and the bottom crossing. Now, if you don't include relaxations, if you go to a smaller angle than this 1 degree magic angle, you can go to say 1/2 degree or 1/3 of a degree or 1/4 degree. What you'll find is that instead of having the first band crossing hybridizing, you get the second order band crossings or the third order band crossings or the fourth order band crossings. And it gives you this geometric sequence of perfect tunings that give you flat bands. However, when you include relaxations, that doesn't occur. So this variable here is the Fermi velocity. It's basically the slope at the Dirac cone. And you can see that that Fermi velocity is going to 0 multiple times in both the original model from Alan McDonald's group, as well as our unrelaxed model. When you include the relaxations, those touching points kind of are prevented. And the reason for that is because of the atomic relaxation. At small angles, you're no longer able to create a smooth Moiré potential. Instead, the local structure of these AA spots becomes fixed, so the potential well is always the same shape. So you're not able to tune this harmonic oscillator like Dirac cone state any smaller because you're not able to make the well any bigger than this size. If you try to make it bigger, the atomic relaxations will push it and compress it into this nodal structure. Okay. So my last few topics are just other ways you can control these Hamiltonians, and then I'll spend about 5 minutes talking about ways this connects to topics in quantum information, general relativity, and supersymmetric field theories. So this one will be fast. Okay, how can we change the Hamiltonian? Well, number one is pressure. If we make the layers and push them closer together, the tunneling gets stronger. And if you make the tunneling stronger, the condition for the magic angle changes. So these are band structure calculations. The top axis is the twist angle. The rho axis is the compression. So a more negative number means more compression. What we can see is that if at 0 compression, you have a magic angle at 1 degree, at about 10% compression, you're going to have a magic angle at 2 degrees. So this is just a renormalization of the Hamiltonian. It's not very surprising. If you make the compression very strong, you increase the tunneling strength, and then you can make the twist angle bigger to compensate for that. And we actually mapped out kind of numerically where we expect the magic angle to go as a function of the pressure. And Corey Dean's group at Columbia actually did a very beautiful experiment where they made twisted bilayer graphene and then fabricated it in a hydraulic press, and they measured superconductivity and Mote insulation at angles larger than the metric angle by using pressure. And the correspondence was pretty good, kind of fits this linear expansion that we have for our model. Okay, another way of creating different types of Hamiltonians and different types of tunneling strengths is by using composite layers. So this was a work I did in collaboration with Chen-Wan Lee and some members of Subir Sasha's group at Harvard. And the idea is that if you have 3 layers of graphene, you can make the middle layer twisted. And now you have a twisted interface on both the bottom interface and the top interface. And you can treat the top and the bottom layer as one effective composite layer. So I have the band structure here for twisted bilayer graphene. You can see there's a flat band and some small gaps at 1 degree. And then this is the sandwich. You can see all the features are still there. You know, this sort of structure at gamma, the flat bands are still there, but 2 things have changed. There's now a Dirac cone behind everything at K, and the angle is about 50% bigger. Okay, so why did this happen? Well, you can do a simple basis transformation to get this out of the Hamiltonian. If we write this as a 3-layer basis, and we implement an bonding and anti-bonding combination between the top and bottom layers, the antibonding combination has a plus and minus sign for the middle layer. And so it doesn't see the middle layer, it decouples from the middle layer's Moiré pattern. However, the bonding combination, the plus sign, sees effectively a factor of square root 2 stronger because it has twice the interface, and then there's this geometric correction that gives you the square root. So when you do this transformation, you end up with a Hamiltonian where you have basically the twisted bilayer graphene Hamiltonian with the factor of square root 2, and then a decoupled Dirac cone Hamiltonian. And the interesting thing is that if you apply a potential between the top and the bottom layer, say with an electric field, when you do this transformation, this on-site potential transforms from a diagonal term to an off-diagonal term. And so now it's actually telling you that the electric field controls the tunneling between the magic angle Hamiltonian and this background Dirac cone. And this has some connections to ideas from the 80s that came up in high temperature superconductivity, which is the steep band, flat band scenario for superconductivity. Basically, the idea is that you have flat bands, which have strong correlations, but very weak phonon electron coupling. If you have a dispersive band that has very weak correlations, but very strong phonon electron coupling, if you could couple the two, then you could create a very flat band with very strong phonon electron coupling, and this would encourage superconductivity. And we're able to basically fabricate that with this sort of construction. At zero electric field, the flat band and the steep band are completely decoupled. And as you turn on the electric field, you can control the hybridization between the states. So this might be a useful platform for studying that proposal back from the 80s. Okay, and this is another example of composite layers. This is 4-layer structures of graphene done by George Twistronics, one of the postdocs in Hexagonal's group. And we did a very large survey of different types of layer alignments. And I'm not going to go through the details here, but I just want to highlight that if you pick exactly the right type of structure between the layers, you can have flat bands with parabolic touching points. You can have isolated flat bands like the twisted double bilayer, or you can have these very complicated bands that are fairly flat but have this interesting symmetry structure, which is probably coming about due to some clever, you can probably analyze why this happens. I didn't do it because it would take too much work, but we did this for a ton of different structures. And you just see a large plethora of low energy Hamiltonians, which is quite nice. Okay, and there's a lot of other tunings. I don't have time to talk about them, but really quick, there's chemical intercalation. You put an atom in between the layers, you can increase the tunneling between those states. So that's kind of useful. When you introduce some sort of substrate like hexagonal boron nitride, like they did for the Hofstadter butterfly experiment, you can open gaps that otherwise would not be able to be opened, and that might be useful for applications or experiment. And actually, the Coulomb interaction, which controls the Motte insulating phases and say the quantum spin chain phases, they're going to be affected by the geometry of the gate. So if you make the gate in your device very, very close to the material, you're able to suppress the Coulomb interaction significantly. And so there's been some proposals that you could study if the superconductivity is caused by high TC correlations or if it's caused by phonon dispersion by making these specific geometries with very, very close gates, because that's going to suppress most of the Coulomb interactions. And so if superconductivity still persists, you know that it's probably not being caused by the Coulomb interaction. It's probably being caused by phonon electron coupling. Okay, and this is just a summary. Basically, we have these different ingredients of the Hamiltonian. We can control them with all these different techniques. It's very exciting. It's very cool. I don't think there's a single person in the world that understands every single way of tuning these, but it's a huge field, a huge number of things that can be done. And as people get better at fabricating these, the hope is that this can create a new platform for studying both different applications, but also different representations of high energy theories. So I'm going to talk about it in my last section, unless there are any questions. Okay, so I'll get through this so we're done exactly at 1. Thank you for the questions during the talk. I really appreciate them. And we'll have some time for discussion afterwards. So the first application is quantum information in these twisted 2D materials. This one's pretty straightforward. You have localized electrons. They have localized states with specific angular momentums. These are basically quantum dot type applications. And the idea is that because you can control the tunneling between these states by controlling, say, the width of these Dirac cones or how much these bands hybridize, you could create a system where maybe you can get a very stable quantum dot on a large network with tunable coupling between the quantum dots. And you could use this for some sort of programming application to program your quantum computer. Now, this is a pipe dream. I'm not saying I know how to do this or that it's going to work, but that's just one of the applications that's possible. Yeah, go ahead.
Well, I think this is quite cheating here, because you don't really know exactly how the entangle of this dot with all the system. So basically, if you want to say that you use this for quantum information, that is really cheating.
Yeah, well, I mean, I don't know what its coupling is with the rest of the system. So you'd have to study the photon-electron coupling and the screening effects and the Coulomb effects and the tunneling to the substrate. But these 2D materials are usually fabricated with extremely high quality, so they have very low defects. And I think it's very likely that in maybe another 5–10 years, they're going to have much higher quality quantum dots than the gallium arsenide systems, which are prone to a lot of fabrication defects, which cause a lot of decoherence. So here, the quantum dots are not fabricated by pattern gates. They're fabricated by the interface between the materials, which is a self-cleaning substrate. That's why they're able to get such good transport quality in graphene.
Well, but my point is that if you think that in terms of like, you think of this as a quantum dot, you need to like single out the information of this quantum dot to do the quantum information.
Of course.
But because of the dot like entangled with the whole system, and you don't know how to control yet.
Yeah. Of course, I'm not saying that I know how to do this. I'm saying it seems like it might be a promising direction in the future. Specifically, if you can find materials where these flat band states are very separated from the surrounding states, they have a very high energy separation. This would be a pretty coherent quantum ground state. But I agree. Yeah.
Okay. Thank you.
Okay. Okay. Number 2, general relativity. All right. So this is a classical treatment of the effective curvature on the 2D crystals. Basically, you have this low energy, this is a bilayer graphene Hamiltonian from this PRB paper, which there's a lot of papers that talk about this idea. I picked this one kind of randomly off the internet, but it's quite a nice paper with nice figures. So it's a good place to start if you're interested in this. Basically, you can write down the graphene Hamiltonian and then ask, what is the effect of curvature? So if you take the Bilayer and you curve it, what does it do to the low energy Hamiltonian? And what they show, and what you can show in general, is that if you treat the curvature as some sort of correction to the 2D metric, it enters as something fairly similar to some generalization of GR to this system. And the way I would think about it is, if you could control this curvature very well, you could imagine the ballistic transport of an electron going through this curved system. And the curvature is going to affect the band structure, and it's going to cause electrons to, instead of traveling in a straight line through the graphene surface, they're going to follow some new metric that's defined by the curvature. And so maybe there's some crazy world where you make a really pristine material and you curve it a lot using some careful mechanical construction, and you can effectively create like a black hole for electrons. You shoot an electron in, it travels ballistically, it sees this curvature and it starts spiraling down into the center. And now the question is, what happens? Obviously, if you do this in an experiment and you continue running the current, you're going to melt your crystal because you're going to put all the energy in one place. But I think it has some interesting connections to some of the black hole ideas, and maybe these ideas of you can measure things in terms of boundary conditions of event horizons in curved spacetime. Yeah.
I may upset you again, but this idea is also not possible.
Yeah, so the difference here is that this was originally proposed in terms of just adding curvature to the Hamiltonians. Yeah. But with a high amount of control, sorry, go ahead.
But the main point is that using the material, you cannot add enough curvature to make black hole.
Of course, I know. I'm not saying that it's possible to make that it's sharp enough to actually collect electrons. I'm just saying this is kind of the idea of how you could try to mimic something. And I know you're an expert on this more than I am, so I definitely defer to your.
Yeah, so I think that's the true idea here is that you can see something like gravitational lensing.
Yes,
so basically
exactly.
You can assume that you can have something like a star in the middle, and you have the wave function go around that. But if you want to do black hole, then it's too much.
Yeah, well, you need I'm not saying it's possible with graphene, because you basically have to break the graphene layer to make a curvature that strong. But yeah, the lensing example is probably better, right? You can send in a plane wave and see how it bends.
But there's another good idea is following way in terms of like Bilayer graphene. You have the graphene with a nanotube between two layers, and you can see that is something like a wormhole.
Right.
That is an interesting idea to do.
So you basically fabricate a graphene layer and another graphene layer, and somewhere in between the interface there is a smooth deformation into a nanotube that connects them.
Yeah.
And this is a way of going from one plane of the space-time to another plane in a smooth way. Yeah.
And you can mimic this as a wormhole. It's very interesting idea.
Yeah, and it comes out of the equations too. It looks like similar to those equations. So I mean, it's restricted, and you have to do some holographic projection from 4D to 2D space-time.
Yeah, that's true.
And the final thing is I'm even less confident about, but I know there are some hints of this in the literature, that you can try to represent some supersymmetric theory within a 2D material Hamiltonian. And so this was an example I found of quantum electrodynamics. And the basic idea is that you have some sort of Hamiltonian. It's defined by, here's the bilayer graphene Hamiltonian again. You have these Dirac Hamiltonians, and this is the tunneling between the layers. And if you do some careful addition of new fields and careful rearrangement of the terms, you can make it look like a quantum electrodynamics type Hamiltonian with the covariant derivatives and with some scalar potentials. And you can also add gauge potentials and non-abelian potentials and chiral potentials. And one of the interesting directions that I'm kind of thinking about now is once you get a really good idea of the different ways you can control these 2D Hamiltonians, are there ways we can specifically engineer these sort of structures using external perturbations to mimic the things that would be needed to test things in supersymmetry? So I'm not saying that doing this will tell you about the details of the universe, but it tells you about what the quantum ground state is. This is sort of a quantum analog of the GR idea. The general relativity idea is a classical kind of problem. This is a more, it's about the, the correlated states that come about from these sort of Hamiltonians.
So how would a supersymmetric transformation look like in this picture?
I'd recommend to read some of the papers on this. It's really outside my wheelhouse, and the equations are gigantic. But basically, this covariant derivative has a normal derivative plus a gauge field, and there's a supersymmetric gauge transformation between that gauge field and the phases of these scalar fields. It's something like that. I don't remember the details because it's not something I'm really an expert on. But the idea would be that you could find situations where there's a certain physical effect that causes the gauge field, and there's a different field, certain effect that causes the scalar field, and then there's a supersymmetry relating the gauge field and the scalar field. That might be kind of interesting.
So can I, for example, like the fermions can play this role?
Sure. If you add a bosonic field, you can say that the phonons are a bosonic field, and they couple in this form to the low energy Hamiltonian using the phonon electron coupling. Yeah. But you can also get scalar fields just from some of the Moiré pattern effects are scalar fields. So related to this topic before about this analytic solution of the magic angle graphene problem, what you have to do to get the analytic solution is you have to send the strength of the scalar field to 0. There's a gauge field and a scalar field. The gauge field controls this kind of the twist angle coupling, and the scalar field basically pins where these AA defects are. And if you turn off that scalar field, you're able to get an analytic solution. So I think there are certain symmetries between those sort of potentials by transforming the basis elements of the Hamiltonian. But again, not my area of expertise. I just know that there are grumblings in the community that this is a way forward. Yeah. Okay, and with that, I'm all done. So today, hopefully, I've given you guys a good introduction to the multi-scale models for these 2D systems. I showed that you can predict the flat bands. I didn't try to predict the correlated states, but you can predict what the flat bands are. And I gave some intuition for the twistronic materials, and I showed how you can make a lot of different types of physics out of these platforms. So I also have a section called pipe dreams. This first one you'll notice is crossed out. So back when I started my PhD and worked on this topic, this first one would basically be my final line in all my conclusions, which is, hey, we can use these Moiré patterns to create correlated states and topological insulation. And we're done. We did that. Good. So now we need to do these other things. Those might take a lot longer because I think this field was pretty well developed when I started working on this topic, but I was very happy to get involved and make some predictions. So yeah. Thanks. This is my acknowledgement slide. Most of this work was done while I was a grad student at Harvard, but I'm continuing it as part of my research here at the BTPC. And there's a long list of faculty, grad students, undergraduates, and postdocs that have helped me along the way. And these are all the funding sources and universities that I interacted with. Thanks.
Great. Thanks, Stephen. Let's give a virtual applause. And we definitely have time for questions, and so feel free to hang out and chat if you like.
It's very, very interesting talk.
Yeah, this is super exciting. Can I ask you real quick about the topological insulator story? So I think I might have missed a little bit. So this is as you tune, or for example, I think there are a lot of, I think I'm getting mixed up, and there's a lot of different parameters.
Yeah, there's a lot of moving parts. Yeah.
So but schematically, as you tune one of these parameters, you're transitioning from this triangular structure to the hexagonal structure. And is a statement that there's kind of a, let's say on the triangular side, I have some set of bands with Chern numbers, and on the hexagonal side, I have some set of bands.
So on
with
both
different
sides,
Chern numbers.
so both of these sides, they're trivial. They're topologically trivial because you can represent them with a conventional insulating model.
I see.
It's the in-between part that's not trivial.
I see. So yeah, here in this diagram, you have this TI point with the three.
Yeah.
So that's where these different bands have come together and merged into some weird kind of higher Chern number band
Exactly.
at that point. I see.
Exactly. Basically, the way you get Chern numbers is by having bands that are isolated that cannot be represented by any sort of realistic geometric type bonding model. And that's one way of saying that you have a Chern number. What it's really saying is that you had these bands that are coming from, you know, atomic or geometric objects, and because of how they hybridize, they've coupled and split from each other in such a way that they're no longer you can no longer separate them while still keeping a conventional view of type binding model physics. And so when you go to the boundary, or when you go to an area that's trivial, or you go to the vacuum, these bands have to talk to each other and invert quality again to kind of unwrap this twisting that's been caused in the topology of the wave functions.
Yeah, interesting.
Yeah. And so usually the way you'll see this is there's these simple two-band models for TIs, and you basically cause a band inversion near where the two bands get close to each other, and that's enough to sometimes give you non-trivial Chern number. It's basically, you sort of think of it like a lava lamp. You have these bands that are like two different blobs of the lava lamp, and they've passed a little bit of topological information to each other. And in doing that, they've become coupled in a geometric way, and you can't undo that coupling without having the information travel back, and that's what gives you edge states and stuff.
I see.
Yeah, this is different than like topological insulation is different than like say quantum entanglement. It's more of like a geometric entanglement. It has to do with the differential geometry of the wave functions.
Maybe I have some quick comment about the high energy application.
Yes, please.
I think that the thing here is that many condensed matter people think about like using this to study some kind of like high energy effect, for example, like anomaly, using the twist and the strain. But there's a problem there. You have the good low energy effective theory. Look like you have the Dirac field, for example, but the theory in condensed matter is UV incomplete.
Right. Yeah.
And then when you study something like anomaly, you need to integrate the you need to integrate the energy to infinite.
Yeah, which doesn't work because the bands, they bend back around and come back down to zero energy. Yeah.
And there are many results published by the condensed matter community is just wrong, because they assume that the Dirac theory is go to infinite.
Yeah. So yeah, if you have to decorate to infinity, if you have to do the UV completion to get your singularities, then it's never going to work. I agree with that.
Yeah. So basically,
well, I mean, but sorry, I mean, an anomaly you should be able to get from some IR considerations directly as well. An anomaly doesn't have to be.
Not really. Basically, for example, triangle anomaly, you need to integrate the loop, integrate the momentum in the loop to own momentum to get the correct like my anomaly. And if you assume that your graphene can mimic that, it's not the correct statement. But there's many publications imply that they can measure the anomaly, they can measure the high energy anomaly using graphene, and it's not correct statement. Your theory is not UV complete. In the same sense, is that when you strain graphene, you have the magnetic field, but because so you're saying that you can have like current, like quantum hole current inside, but it's also wrong statement. You can only have the valley current, and the reason because when you go to the high enough energy, the two valley connect to each other, and destroy the quantum Hall current.
And also the curvature doesn't break time reversal symmetry. So what the
Yeah,
curvature
yeah.
is, it's a non-abelian gauge field that satisfies time reversal symmetry.
Yeah,
So it's
yeah,
like a magnetic
that's it.
field, but it's not.
Yeah,
Yeah.
it's not. Yeah, and basically, I had a dream that I can do many things with. I can mimic high energy with something like graphene, but now I see that I go to like big trouble if I try to push too hard.
Well, my
But the
point
low
here
energy
is,
physics still there. Low energy.
yeah, my point is that here that you have a limited number of things you can change in graphene. But as you start making these more complicated structures, you have these very complicated 2D Hamiltonians, it's possible to introduce things that are not there for the monolayer. That was kind of my idea.
But you need to limit yourself to the low energy phenomenon.
Yeah.
You should not do high energy. That's too high energy. That is not correct.
So, sorry, with this Suzy QED you have here, this is just, it's 2 + 1 dimensionals, right?
I think so, yeah. I'm trying to remember there's a ton of different papers about this. I think there are some people that argue that you can have it as a hologram of 3 + 1, but I don't know the details because I didn't have time to read all the math. But yeah, it is 2 + 1. You have the time variable, and the time variable gets tilted depending on the angle you cut through the Dirac cones, which is like these world lines you would have for a normal Dirac fermion in free space.
Would it be possible to think that one of the effective degrees of freedom that exist, I guess maybe the case of with the connection with gravity that you mentioned, is a spinor vector?
A spinor vector potential or something? Or a spinor vector as the degree of freedom itself?
As a degree of freedom.
I mean, if you look at graphene, I mean, this is the spinor.
Yeah, I know, but maybe one of the that's what I'm asking. One of the other states, or in some special configuration of the system, with all these parameters that you have, you can make a quasi-effective degree of freedom, which behaves as a spinor.
I don't know very well what a spinor vector is, so I can't answer your question.
No, it would be a spinor that has a vector index, like a vector, like the gauge vectors.
So these are scalar spinors. Yeah, I see.
Yeah.
Okay.
So that would be huge.
I'm wondering, is that related at all? So there are certain. Let me talk about the topological insulating again. There's this. Yeah, so this paper here basically talks about how you can get topological insulators in these twisted transition metal dichalcogenides. And it explains it a different way than I explain it. It explains it as an effective skyrmionic texture in the spin degree of freedom, or in the quasi-spin, the valley degree of freedom. Basically what's going on is, if you look at these potentials, one of these is a gauge potential, the other two are scalar potentials, and you can put them together into a 3-dimensional vector potential. And you can show that these topological insulating states are actually, they're topologically insulating because of this fuzzy ball theorem for the skyrmionic texture of that object. So I wonder if that would be closer, because I know that has a vector, that has a degree of freedom with a vector form. I don't know what the, I don't know if it's a spinor or not. It's been too long since I read the paper. Yeah, but
because the existence, just the existence of such a thing, that would be huge for both supersymmetry and gravity, among other things.
If that can actually exist anywhere in nature.
Yeah, yeah.
Interesting.
Because that's the only. So from the list of particles, that's the only thing, the Rarita-Swinger fermion, which is a spinor vector. That's the only thing that has been observed, and it's related with supersymmetry. And I was always imagining that a condensed matter system, that you have so many knobs that you can bring the system into so many different configurations, would be the one that can reveal such a behavior.
My guess is that if that was to succeed, it likely would not happen at the single particle level. Like it wouldn't come out of the single particle Hamiltonian.
Right.
It might come out of
be an effective. It
Exactly.
will be an effective collective description, but the system will be in such a phase that you will can identify it as one propagating degree.
Exactly. Yeah. I don't know enough about the topics in GR and high energy theory to know exactly what the structure of that object is. I don't know my standard model very well.
It's not in the standard model.
I know, but I don't know the different types of enumerations of types of particles to be very confident when you say, oh, a spinor vector particle. I'm like, oh,
so basically, it's no big deal. Just taking the spinors that you have and add to
give them a vector index. I know.
Yeah, vector index.
So kind of my point with these slides here is that I want ideas like this to try to look into, and because I basically have no answer for you right now. It's definitely a cool idea. Yeah.
Another way to think about it would be a gauge fermion.
Okay. Yeah, a fermion with a gauge. It's a derivative of something. Yeah.
Right.
Okay.
So yeah, this guy's supposed to be the super partner of graviton.
Mm-hmm.
So spin differs by half from 2, so 3 halves.
Because there's bosonic vectors. Okay. Vector particles.
So, kind of along the lines of this gravity connection. So the kind of setups you're envisioning here, or that is there any simple way to kind of model kind of the time dependence of the geometry, or is it kind of more like I have some fixed 2-dimensional geometry?
Yeah, it's kind of like you bake in it's not going to be the coupled PE. It's going to be you bake in a geometry and see what happens. Okay. I'm not sure if that's always the case. Maybe there's some weird effective thing where maybe it's not the curvature that causes you to have this curved metric. Maybe it's something to do with like the temperature or the phonon density or something. And maybe there's a situation where the motion of the electrons or the motion of the phonons causes that thing to change as a function of time. And then you get this coupled nonlinear GR thing. This is just talking about getting non-Euclidean curvature into your space-time.
Right.
Yeah. Thank you. Yeah.
I think there's paper where they study the deformation, but time-dependent deformation. In this case, you can have the curvature depend on time.
But is it sourced by the particles, or is it an external force? Because if it's not like sourced by itself,
it's an external force.
Yeah. Okay. Yeah.
They
so
change
it's like fake GR.
They deform that, and basically they can make. So, but basically, the story is that when you study the strain graphene in the way that we do. You form this thing, you only have the magnetic field, but you don't have the electric field.
Right.
But when you deform this time dependent, you can have the fake electric field also.
Right. Okay. So you get a scalar term that comes out of the time dependence of the curvature. Yeah.
I see. And you see some very interesting current in this thing.
Yeah. So basically they do that by some mechanical setup where they have some piezoelectric that's shaking the thing.
Basically the thing that you don't need to make a curve to have a magnetic field.
Yeah,
you can make the non-uniform chain, you have a magnetic field. Basically they do that is that they have the graphene here.
Yeah.